If I ask you to build a calculator from scratch using only switches that are either on or off, so ones and zeros, how would you handle the negative numbers? It seems simple. Maybe we just use the first bit to say minus and the rest to say the number, right? Well, there is a problem with that. If you do that, addition breaks. You need a second, more complicated circuit for subtraction. But what if I told you there is a way to represent negative numbers so that the hardware doesn't even know they exist? A system so elegant that the chip just keeps adding and the negativity works itself out automatically. It's called two's complement, and understanding it is like seeing the matrix. Today we're going to look at it under the microscope, look at how it works in C++, and explore why we can call it also the domino effect, where carries just disappear. Now let's start with a naive approach. Let's say we want to store the number 7 in an 8-bit integer. Here's how the bits would look like. First one is 2 to the power of 0, second is 2 to the power of 1, and this one is 2 to the power of 2. And this will result in 4, 2, 1, which is 7. And that's simple. Now, if we use the sign and magnitude, this thing here, so to the power of 0, to the power of 1, to the power of 2 to the power of 2, if we use this method and just flip the first bit to 1 to make it negative, if we do this, and this now becomes negative, it looks logical, right? But here is the problem. Let's try to add 7 and minus 7. And we get this number, but that would be minus 14 in sign and magnitude, not 0. It doesn't work. And worse, we have negative 0. That's negative 0. But we also have 0. And we've just wasted a combination. So the hardware engineers needed a system where addition just works, regardless of sign. Enter 2's complement. 2's complement works on one simple principle, modulo arithmetic. Imagine a car odometer. So if you are at 000 and you go backwards 1 kilometer or mile, it will roll to 999. In binary, we want the same thing. To get the negative of a number, we use a simple algorithm, flip the bits and add 1. Let's prove why minus 1 ends up as all ones, and let's start with 1. That's the number 1 in binary, and the algorithm is flip the bits and add 1. So this will become, and we add 1, and it becomes all ones. And that's why when we write int x equals minus 1, this results in a bit pattern of all ones. It's not a random choice, it's a mathematical necessity. Now, here is where the domino effect comes in. Watch what happens when we add 7 and minus 7. This is 7. First, let's calculate minus 7. We take the number 7, and the algorithm is flip the bits and add 1. This will result in this. So that's minus 7, and this is 7. Now, let's add them. The algorithm is as follows. 1 plus 1 equals 0, and we carry 1. Let's do this for this and this number. So 1 and 1 equals 0, and we carry 1. So we carry 1, and this is 0 plus 1, but we carry 1, so that's again 0, and we carry another 1. And that repeats. 0 plus 1 plus carry, that equals to 0, and we carry 1. Then we have 1 plus 0 plus carry, that's 0, and we carry 1. And we continue in this manner, like this, until we get to the 8th bit, and it ripples all the way through the bits until it reaches the final bit, the 9th bit, and that final carry, that one tries to go into the 9th bit, but it just disappears. The CPU ignores it. The domino chain collapses, and we are left with all zeros. The hardware didn't need a separate subtract circuit, it just added, and the overflow handled the negativity for us. Now, let's get into the weeds. This is where C++ and low-level programming get interesting. What happens when you have a small negative number and you try to shove it into a bigger container? This is called sign extension, and let's see what the compiler is doing. But first, the issue is that this is short and it's usually 2 bytes or 16 bits. We set it to -1, so it fills with all ones. But then we have int x equals I, and the integer is 4 bytes, so 32 bits. When we assign I to that, what happens with the remaining 2 bytes? If the computer just padded it with zeros, fill the extra 16 bits, what will happen? It will happen 2 bytes of zeros and then followed by 2 bytes of ones. And that will be a whole lot of a different number than -1. And we expect x to be -1 here. And because C++ respects the integrity of the number, it doesn't pad with zeros, it performs sign extension. And we can see it in the assembly here. We see the value -1. We can see that it was stored at the location RBP -6. And we can see that this is at -4. And we store the word, so that's 4 bytes. And we need 4 bytes here. But then we store just the word here. And a word in this system architecture is 2 bytes. So from 4, we have to add 2 more bytes and that becomes 6. So we store the value -1 here at 2 bytes. Then, and here's the interesting part, we call this instruction, which is move, but also does a sign extension. Here's what happens. It stores in EIX the value that was written into this memory location, which is -1, but it does sign extension. So it will check if it's a negative number or if it's a positive number. It will sign extend. It will add either zeros or ones so that the sign stays the same. Or we can say it looks at the highest bit, the sign bit of the short, since it's 1, meaning negative. It will fill the new higher bits with ones. And we can see on the next line, we take the value, the now extended value here. Here we perform a move, again, the word, double word. So that's 4 bytes. And here's the interesting part. This will be an integer, so 4 bytes. But why is that -12? The value has to be a multiple of 4 when it comes to integer, and it's addressed in memory. We can't put it at value 10, for example, because that's not multiple of 4. That's just how the compiler arranges memory. For example, the short, which is 2 bytes, it has to be a multiple of 2. And we can see it stored at the location, which is 6 here. That's why this is 12. It basically is padding 2 more bytes that can be here. And what we can see, so EIX, which is now extended -1, it is written in this address, and we have a copy of -1, just in a different address. That's how the compiler does it. It uses move sign extension. Now let's check that with another architecture. Let's check it with ARM, and let's use ARM GCC. What we see here, it has more instructions. This is the -1 value, and here is what's happening. Here we store -1 into R3 register, this one here. Then we take the R3 register, takes the value -1 here and stores it here. So we have at R7 a -1 value there. Then again we use R3. This instruction says it will take the value here and store it in R3, but it will do sign extension. So again, in R3, we say we store -1, but now it's sign extended. And here we store again that now sign extended value into R7. And yeah, that's the end of the example here. Now let's get back to Quank x64. Now, what would happen if we use bigger container and store it into a smaller one? So this example, but the opposite. First, if we have this warning enabled, it will say that we have an implicit conversion losses because integer is a bigger container than short. But let's check the assembly. It's similar story. We have the value -1 stored into this location. Notice this is now at 8. So we have 4 bytes, which is how it should be. Then we use EIX and we write the -1 there as well. And these are the words, so double words. And notice this, we use the move instruction, but instead of AIX, we use IX. And we store it at 10, which is fine for a short. But notice what happens. The compiler warns us about. It will basically cut the 2 bytes from the end of the integer, and it will store it in this memory location here. So that's why this is not that safe conversion. And similar thing happens with another architecture. Let's check again ARM. And with ARM, we can see the similar story. We load into R3 the -1 value. Then we store R3 value into R7 with some offset. Then we load it again. So we load whatever we just stored here into R3, and we store again that value into R7, but it is now converted. If you found this deep dive helpful, hit that like button. Thanks for watching, and I will see you in the next one.